Hello and welcome to 2010. We're kicking off this new year with the launch of a brand new programme called Naked Astronomy. The show's supported by the Science and Technology Facilities Council, who support UK space science, and also by Cambridge University's 800th anniversary team. With the help of both of them, we've got together a group of budding space scientists to help us take a look at what's out there. Naked Astronomy will come out every month. You can get it free from iTunes or from our website at thenakedscientist.com/astronomy. Right now, time for liftoff.
Thrusting space science into the audio dimension. This is Naked Astronomy.
Hello and welcome to Naked Astronomy, a new space science podcast from the Naked Scientists. I'm Ben Valsler, and each month I'll be delving into the latest astronomical and cosmological news, meeting some of the world's finest space researchers and tackling your cosmic questions. This month we'll be hearing about the first light data from the Planck mission, the mapping of Mercury, and why NASA revisited the moon, both to smash a rocket into it and to take some photos.
Yeah, so they've taken several images, and it depends on how the sunlight's striking the surface. And some you can actually see the pads of the lunar module from Apollo 11, those famous pads that Neil Armstrong stepped from.
We're joined by Professor Ian Wright to talk about the challenges of intercepting an interstellar object.
The comet is probably something like a kilometre or two across, and you've got a multi-billion kilometre journey to get there, and then you've got to find it and ultimately land on it. It is amazing.
And David Clements explains how it's not just visible light that astronomers are interested in.
So to really find out the true history of the universe, if you just look in the optical, you only get half the story. And by operating in the far infrared with Herschel, we will begin to see what the other half of the story is and get a real clear picture for the first time ever of the history not only of star and planet formation in our own galaxy, but also the history of galaxy formation and evolution and the missing 50% that we can't see because dust is in the way.
Plus, we answer your questions on galaxies, quasars and general relativity. So if you've got any questions, feedback or comments for us, let us know by emailing astronomy@thenakedscientists.com.
Supported by the STFC and Cambridge University's 800th anniversary team, this is Naked Astronomy. For more information, look us up online at nakedscientist.com/astronomy.
Now, let's meet our expert panel for a look at the latest news in astronomy and cosmology. We'll be hearing from Carolyn Crawford, an astronomer at the Institute of Astronomy in Cambridge, and from Dominic Ford, who works in the Cavendish Laboratory. But first, Andrew Ponson, researcher at the Kavli Institute for Cosmology, tells us what's been exciting him recently.
Well, one of the most exciting things is the Planck mission, which was launched all the way back in May. But the reason it's come up again recently is because we've got what we call the first light data coming back from the Planck satellite. So the first light data means it's the first light that it's collected on part of its science mission.
And what's Planck really there to measure?
Well, Planck is measuring what we call the cosmic microwave background. Now, that's light. It is in effect light, but it's become microwaves as the universe has cooled down. Microwaves, just a type of light. But it's light that was really produced in the first few 100,000 years of the universe's existence, which is really a very small amount of time in terms of the billions of years that the universe has been around for. So the idea of the Planck mission is that we map out this light in ever more detail and find out what was going on right at the beginning of the universe.
I assume that first light is important not just because you're actually starting to collect data, but also because it shows that everything works.
That's absolutely right, yeah. So the idea is that we measure this in lots of different bands. So in other words, we pick up light of different frequencies. And it's really nice to see that all the different detectors are working really well and nothing's been broken on launch and everything is coming together much as it should do.
So that's measuring something that happened billions of years ago when the universe was very young, but also we're looking at things in a bit more detail. Carolyn, what's caught your eye recently?
Well, it's been a very good month or so for exploration within our own solar system. There's been an awful lot going on. Right from the recent flyby of the Rosetta spacecraft, which we'll hear more about in the interview later on in the programme, but you could start with the most recent flyby of the planet Mercury, because Mercury's been quite a neglected planet in our solar system. It's the smallest, it's a very hot, dry planet, it's close to the sun, and we haven't actually sent spacecraft there for a long while. Well, there's this fantastic spacecraft called Messenger, which is due to revisit it. And it takes a long journey to get there. It doesn't just go straight to Mercury and settle into an orbit around it, but it has to do a number of flybys, they're called. And the main aim of these is you accelerate the spacecraft, you give it enough energy that it can then settle around back into a proper trajectory that takes it into an orbit around the planet. Now, it's going to do that in 2011. But the interesting thing is it's done 3 flybys of Mercury, and they actually keep all the science instruments operating as they fly past, and they've been gathering data already. And it's really whetting our appetite for what it's going to be like when eventually we're settled down to a continual mapping.
So what sort of things are we hoping to find out?
Well, first of all, they've been mapping the surface. They've been taking these fantastic pictures of the craters and the plains on the surface of the planet, beautiful images of double ring craters, and there's unusual sort of textures within the surface that they don't really explain yet. So you're looking at the surface. They're also measuring what is in the surface, what the concentration of heavy elements, things like iron and titanium are. And there have been a few surprises there that they're much heavier than they expected. And then one thing it's been measuring, which I always find amazing, is the atmosphere of Mercury, because you'd think so close to the sun Mercury wouldn't have an atmosphere, but it does have a very tenuous one. It's made from atoms that are blasted out of the surface by the very strong UV radiation from the sun. And so you have like this cloud of atoms of sort of sodium and calcium, magnesium, and they kind of tail away behind the planet. And what's been interesting is that in each of these 3 flybys, they found differences in both the extent and the density of the atoms in this atmosphere. So it looks like there are sort of seasonal changes as Mercury goes round its orbit around the sun, that the atmosphere of Mercury changes. And that obviously is going to be tied to how the atmosphere is generated in the first place. So this is just from 3 flybys. It's going to be very exciting to see what happens when Messenger finally settles down into that proper science orbit, where it's going to spend a good year collecting more complicated data about the surface.
Well, that's fascinating stuff. Dominic, can I bring you in here? What do you think about this?
So something that really surprised me when I started reading up on the Messenger mission was actually how little we knew about Mercury before Messenger was sent up. We hadn't actually visited Mercury since 1974, and of course Mercury never gets more than about 30 degrees away from the sun from the Earth, so it's very hard to observe with ground-based observatories. So actually we'd only mapped 45% of Mercury's surface before we sent Messenger up. And as we've been making these flybys that Carolyn talked about, we've been gradually mapping more and more of the surface. And I think on the second flyby we've mapped 92% of the surface. We're now up to 98%.
Yep,
so that
right.
means there is only 2% of the surface left, which is not mapped. And obviously when we have a complete map of Mercury, that will be the last of the inner planets that we have a complete map for. And it is quite surprising that we haven't mapped Mercury before, because it's quite a similar planet to the Earth in many ways. It's the only other inner planet that has a strong magnetic field like the Earth's magnetic field. We think it has a big iron-rich core like the Earth, and unlike Venus and Mars. So in many ways it's an important planet to understand. It's one which is very similar to our own.
This isn't the only flypast in our solar system. Recently, I understand something's been past Saturn's moon Enceladus, which in itself is a fascinating place.
Yeah, well, this is the continuing adventures of the Cassini mission to Saturn, and it's been doing a number of these flybys. It's a very good way to study the moons of Saturn. I mean, yes, sometimes it gets the acceleration that sort of helps it get into particular orbits around the moons and Saturn, but again, it uses them primarily for scientific purposes. And there's going to be one flyby later this month, and there was one at the beginning of November as well. And it's flown over Enceladus before, and Enceladus is this icy moon around Saturn, and there are large fractures within the ice. And it seems like there's stuff that's sort of venting out from these fractures and forming large plumes that extend into space. Well, this latest flyby Cassini actually flew through one of these plumes. And the idea was to analyse what they're made of, looking at the sort of the charge, the mass, the size of the particles that are generated, and really getting a better idea of what they're made of and what the density of these plumes are.
This is an interesting follow-up on the previous flyby a couple of years ago, when Cassini flew past the night side of Enceladus so that the sun was eclipsed by Enceladus, and it saw reflected sunlight in the plume of material, and NASA got a really very compelling image of this plume of material coming out of Enceladus' surface. And it's thought that this material is actually filling up the F-ring, which is one of Saturn's rings. It's always been a puzzle in the past where the material in the rings has come from, and we think that finally we have seen the source of at least one of the rings in Enceladus.
And particularly with the F-ring, it's quite a fuzzy ring, isn't it? If you look at some of the other rings around Saturn, they're very sharply defined, but that's a much more sort of diffuse structure, isn't it?
Yes.
And am I right in thinking that Enceladus is one of the places we should be looking in our solar system potentially for life? Because it's icy, but apparently there may be great oceans under the surface.
Yeah, it's one of the places where we think there's a large supply of liquid water, and perhaps underneath this icy surface there's a warm ocean. And you might ask, how does it stay warm when it's out in the deep freeze of space? But this little moon, it's quite close to Saturn. It's got a lot of what we call gravitational heating. It's being tugged by Saturn. It's being tugged out by the other moons. So the inner core of the planet is kept very warm. And so potentially that can heat up from the inside and keep any ocean underneath this ice warm and liquid. And many decades in the future, it might be a very good place for us to go and visit, especially, say, if we could melt our way down through the ice and perhaps send a little submarine down to explore the oceans. I think that's a lovely idea.
Water is one of those things that always seems to capture everyone's imagination when we find it out in space. In fact, the L-Cross mission, I believe, was looking to blast frozen water off the moon.
Now, this was actually quite a spectacular explosion. NASA took a spacecraft, which they launched back in June, and they smashed it into the surface of the moon at a speed of 1.5 miles per second. And this was all done deliberately. The idea was to vaporise the surface of the moon, create a crater and throw up lots of material that they could then take a spectrum of and try and see what the surface of the moon was made of. Now, they were doing this into the pole of the moon, which is not an area that they've explored before in the Apollo missions, because they thought that there might be ice lurking inside some of the craters down there. And if there were to be water ice in those craters, that would be potentially very interesting for future manned missions to the moon, because obviously that water could be used as drinking water for the astronauts.
It sounds really interesting, but it seems a very destructive way to measure something. How do you actually tell from the sort of cloud of bits that you've blasted off the moon what's actually there?
Well, the trick is in a technique known as spectroscopy, and this is used all over astronomy and actually in all sorts of other areas of physical sciences. And what you're looking for is the fact that certain atoms, so for instance you could take water as an example if they're looking for water there, certain atoms vibrate at a certain rate. They have certain vibrations that they like to undergo, and that's just to do with the way that they're held together. And when you get light of a certain frequency, it's just a certain colour to you and me, when that hits one of these molecules, it can be very efficiently absorbed by that molecule because the molecule likes to vibrate at exactly the right rate. So they're using that fact, and they're using the light that is passing through the cloud, and they're seeing which frequencies are being particularly absorbed by the cloud to work out what's there, and they can infer the presence of water or hydroxyl ions and so on, and tell us something new about what the moon's made out of.
Don't you run the risk of breaking stuff apart when you slam something into it this hard? Surely some of the compounds that would be there might get broken down by the heat of the reactions, and so we'll detect some stuff that really might not actually be there on the surface.
I think that's absolutely right. It's all a big detective puzzle. So obviously you have to take into account that when you hit something, you can cause all sorts of funny physical changes, chemical reactions and so on. And so what you're looking for is the aftermath of that, and then you have to work backwards to work out what could have been there in the first place.
I was interested to read that one of the things that NASA are worried about is that the L-Cross impactor may have picked up some water in transit through the Earth's atmosphere when it was launched. And so to make sure that there wasn't any ice stuck to the side of the spacecraft, they actually rotated it around 360 degrees so that the sun would bake all sides of the spacecraft and hopefully vaporise any water that might be stuck to it.
This is all the start of really the American NASA, space agency. It's the first steps really back to the moon. They have this vision for space exploration, which, as Dominic says, means we're going to be sending crewed missions to the moon in a few decades. So the LCROSS, it's determining whether there is water ice that possible astronauts could use in the future, but it's all part of a mission to look for potential landing sites as well as hidden water ice, because there's another spacecraft that went up on the same rocket called the Lunar Reconnaissance Orbiter, and that is now settled down to an orbit about 50 kilometres above the moon, and it's taking these fantastic images of the moon, like Messenger around Mercury. It's mapping the moon's surface in beautiful high-resolution details. You're looking at individual boulders, you're looking at young craters, and some of the images it's been sending back, it's gone and mapped the Apollo landing sites. And there are images of all the debris left behind by the astronauts. So they discarded lunar modules. There are old surface experiments left on. And you can look at the image of the Apollo 11 landing site. And the LRO has even picking up very faint tracks left by the astronauts on the surface of the moon. So not strictly scientific, but still fascinating to see these pictures.
I think it was Apollo 17 where the astronauts travelled some distance from their landing craft, and you can see this very clear line of something or other on the moon, which is clearly their footprints to where they laid down the experiments.
Yeah, so they've taken several images, and it depends on how the sunlight's striking the surface. And some you can actually see the pads of the lunar module from Apollo 11, those famous pads that Neil Armstrong stepped from.
That was Carolyn Crawford, and before her, Andrew Ponson and Dominic Ford with a roundup of space science news. They'll be back later on to tackle your questions.
Expand your mind and Neptune in. Naked Astronomy, the stellar space science show. For more episodes of this programme, look us up online at nakedscientist.com/astronomy.
Still to come, Dave Clements explains why it's so important to view the universe at infrared wavelengths. But first, I spoke to Professor Ian Wright from the Open University about the Rosetta mission. Now, this may sound like science fiction rather than science fact, but Rosetta is set on course to land on a comet. It's recently done its final flyby past Earth, and so Ian explained the goal of the mission.
The Rosetta mission is a dual spacecraft mission which aims to send both an orbiter spacecraft and a lander spacecraft to rendezvous with and ultimately land on a cometary nucleus. Because of the distances involved and the speeds involved, it's not possible to just launch from Earth and hope to get there directly. One has to travel around the solar system a few times, building up speed by having gravitational encounters with planets like the Earth and Mars, and then getting flung out into sort of deeper space and ultimately getting fast enough so that one can catch the comet up.
It sounds like there's a lot that can go wrong. You're relying on this sort of slingshot effect around lots of different planets, and then you're catching something relatively small, a comet, millions of miles away.
It is quite daunting in a way. I think having been involved with a mission to Mars where, you have something the size of a planet and it's something you can actually, see quite easily from your back garden when conditions are appropriate. Landing on a planet seems relatively straightforward. The comet is probably something like a kilometre or two across, and you've got a multi-billion kilometre journey to get there, and then you've got to find it and ultimately land on it. It is amazing, and of course, in that sense, I'm in the hands of the spacecraft flight engineers who are experts in this field.
And when did it actually launch?
It launched in 2004. It's already been travelling a few years already, of course, building up speed. It's now going off into a hibernation phase where it'll be effectively in deep space, ultimately hoping for a rendezvous and land towards the end of 2014.
And once it hits its target, once it lands on this comet and sets the orbiter around it, what are we hoping to learn?
The first thing that's quite interesting is, of course, one talks about an orbiter, but actually you cannot really orbit a comet. It's so small and it has no gravity. So one of the first challenges is really to understand how to fly with it. So the whole concept of orbiting is quite strange. In answer to the question, you can think of this as, as a human being, if you're on Earth and you were going to visit a new country that you'd never been to before, you'd have all kinds of questions that you'd want to know about the place. What's the weather going to be like? What's the temperature? What's the geography? What's the terrain? And in a human context, what are the people like? What's the food like? And all that kind of stuff. Actually, you can pose very similar questions in relation to the comet, although we don't expect any humans on the comet, obviously. But just simply any question you can think of about somewhere you've never been before. What does it look like? What colour is it? How cold is it? How active is it? Does it rotate? What's it made of? What's the surface like? Any of those questions, simple or fundamental questions, you can pose about the comet. And the Rosetta mission has been designed to try and get answers to as many of those questions as possible.
Most space missions are actually very specific. They're out there to look at certain areas of electromagnetic radiation or to look at very key things. It sounds like Rosetta is actually trying to be a bit of a jack of all trades.
I don't think Rosetta is particularly any different in a planetary exploration context. I think what a lot of planetary missions have is the widest diversity of instruments that they can possibly take. So, for instance, you want a camera, you want spectrometers, you want things that can detect magnetic fields. And once you get down onto the surface, you want to know what's the constitution like. Physically, what's it like? Is it hard? Is it soft? It's not simply a mission that's going to go to a comet and take a picture of it. It's a mission that goes to ask many different questions. The order of magnitude for the number of instruments is something like 20. I mean, there's like 10 on the orbiter and 10 on the lander, all different instruments designed for different purposes. It's quite possible that they won't all work. I mean, there's a certain amount of redundancy in this. So, one hopes the mission will be successful, whatever happens.
It's a very long way to travel if it turns out not to work. Is there anything that we can use it for on the way? Can we pick up bits of information about the environment it's travelling through?
Well, yes, it is interesting. And although I'd said previously it was about to go into hibernation, actually, it's got one more stop. It's going to fly past an asteroid. It'll be the second asteroid it's gone past during this phase. And yes, we use the opportunity at that point to turn some of the instruments on. Again, take photographs, look at magnetic fields and so on. Again, the mission was designed so that it would actually do this along the way, so that, yes, it spreads out some of the scientific interest along the mission itself. Because as you say, 10 years for a space journey is a long time, and it's a long time to get somewhere and find things don't work. So the mission has already done some science, and as I say, we'll continue to do some next year. Then hopefully next stop, the comet.
Now, thinking more specifically about the instruments on there, you're responsible for the instrument called Ptolemy. What does that actually measure?
Well, some of us are interested not merely in the chemical composition of things, because in a way, I think we already know at this point that comets are made out of things like water, ice, and organic compounds and all those kinds of things. We know that from previous observations from Earth or from space telescopes or whatever. So it's not just about the chemistry, although in principle what we're talking about is getting up close and measuring the chemical composition in as much detail as possible. But it's more than that. It's about understanding the relationship of the materials that are in the comet to equivalent materials from around the solar system. And that's quite challenging. The bottom line here is, okay, if there's water in a comet, how does that relate to the water on Mars or the water on Earth? Is there any relationship? The problem is if you just think about this in terms of water, well, water is water, and it looks the same, probably wherever you are in the universe. And so what we're going to actually do is try and measure the isotopic compositions of the components in the cometary nucleus. By isotopic compositions, I mean things like the oxygen isotopic composition of the water, the measurement of 16O versus 18O, or the measurement of deuterium and hydrogen in the water. And on the basis of those measurements, see if we can connect with the water reservoirs that we know on Earth or on Mars and so on.
So by looking at the ratios of different isotopes, we can tell if, say, the water on Earth came from comets?
Well, you'll never be able to say that. You might be able to say that the isotopic compositions are the same, and therefore your interpretation might be that the two are related. Or, of course, they might be substantially different, in which case you can probably say, well, yes, they're not related. But that does, yes, give a flavour of the kind of ambitions that we have with the mission to give evidence to those inquiries.
Well, as you've mentioned earlier, it's still got billions of miles to travel. When do we actually expect it to touch down?
There is actually a formal date for landing, which I can't off the top of my head remember, but it's sometime in around November in 2014. I mean, what we will do for the few months before that is fly alongside the comet, just observing it and looking at it and really deciding, where is a good place to land. And this is quite an interesting challenge because the engineers will want to put it somewhere as safe as possible, the darkest, flattest place they can find. Whereas, of course, the scientists will want to go to the bit that's got active jets coming out of it, where there's, lots of interesting activity going on. So there'll be a big debate about what landing site we actually select. Now, of course, it's not a very big body, so it's not got a very big surface area, but one can imagine it will be quite varied, and there will be all kinds of different opportunities depending on where one lands. And one can only land in one place. I mean, once it's gone down, it gets anchored to the surface, hopefully, and doesn't come back off again.
Professor Ian Wright from the Open University explaining the challenges and opportunities for landing a spacecraft on the surface of a comet. Landing on distant objects is a great way to learn about them, but sometimes the things that we want to observe are not quite as tangible. Clouds of dust in space obscure our view of distant stars and galaxies, but when viewed in the infrared, they tell a fascinating story of their own. Dr. David Clements is a lecturer in astrophysics at Imperial College London and works on the Herschel Space Telescope.
Well, Herschel is a far-infrared space observatory. It was launched the 14th of May this year, 2009. It's been spending the subsequent 6 months being commissioned and checked out in orbit, and we're currently in what's called the science demonstration phase, which means some of the very, very first science observations are being taken right now. We're beginning to see scientific results and getting ready to announce some of those in the middle of December at a big meeting that ESA is organising in Spain. You'll have already seen perhaps some of the initial images that were produced, which were really very, very quick snapshots done of famous objects or bright parts of the sky in our own galaxy. But those are showing incredible promise for what we expect to be an immensely successful mission.
And specifically, what is Herschel looking at?
Well, Herschel is an observatory, so essentially it looks at whatever the users want to point it at. But it operates in the far infrared, so from wavelengths of about 70 to 600 microns. And this is a particularly interesting but difficult part of the electromagnetic spectrum. It's difficult because the atmosphere is completely opaque at this range of wavelengths. There's a couple of very small windows at the longer end of that wavelength range, which you can get at from very high and dry sites on the Earth. So, for example, Mauna Kea, where the James Clerk Maxwell telescope is based. But essentially, if you really want to do far-infrared astronomy properly, you need to be in orbit above the atmosphere so that you can see whatever wavelength you want. The other unique feature is it's got the largest primary mirror of an astronomical telescope ever launched into orbit. 3.5-meter mirror. It would be a creditable-sized mirror on a ground-based telescope. To put something like that up into orbit is an astounding engineering achievement. The Hubble mirror, for example, is only 2.5 meters across. It really is a massive construction and quite an achievement of European industry to get this thing built and in such a way that you can launch it into space. So that's some of the background of the technology and where we're operating with Herschel. But the reason why these wavelengths are interesting for astronomers is that an awful lot of processes in everything from the evolution, the formation of stars, formation of planetary systems, the evolution of stars, all the way up to the evolution and formation of galaxies, are dusty processes. So you have, for example, in a star formation region, there's a lot of gas and associated dust as the clouds of gas that will form the star collapse. This material gets more compressed, and so it's harder and harder to see through the dust. So if you want to look at these things in the optical, you really can't see what's going on. But by going to longer wavelengths, you can see further through this dust. And also, the dust itself begins to emit by the time you get to the wavelengths that Herschel operates at. The star might be at a temperature of, maybe 5,000 or 10,000 degrees, but the dust, it absorbs all the light coming from the star, but only warms up to, say, 50 degrees above absolute zero, 50 Kelvin. That means its black body emission is just at the wavelengths that Herschel operates at. So we're really seeing the hidden processes of what drives star formation and planetary formation. And in fact, on cosmological scales, which is the kind of thing I work on, we found some years ago that there's a cosmic infrared background. Now, everybody knows about the cosmic microwave background. That's the dull 2.7 Kelvin glow that's left over by the Big Bang. But we find that there's also a ubiquitous background, peaking at wavelengths of about 170 microns, so just where Herschel operates. And what this background comes from is the combined emission of a whole bunch of dusty galaxies which put out almost all of their power at far infrared wavelengths. And it turns out that these objects account, or the energy that you see in the cosmic infrared background accounts for about 50% of all of the energy generated in the universe since the Big Bang. So all of the energy that's produced by fusion in stars, by matter collapsing onto supermassive black holes, 50% of all of that energy is obscured by dust. You can't see it in the optical. And the dust heats up and re-radiates it in the far infrared where we can see it with Herschel. So to really find out the true history of the universe, if you just look in the optical, you only get half the story. And by operating in the far infrared with Herschel, we will begin to see what the other half of the story is and get a real clear picture for the first time ever of the history not only of star and planet formation in our own galaxy, but also the history of galaxy formation and evolution and the missing 50% that we can't see because dust is in the way.
This seems vitally important, and if we were missing 50% of our information about the universe, why has this mission only started in 2009? Have people been trying to look at this particular range of wavelengths before and just not had the technology?
There's a reasonable history of infrared space telescopes and also work from the ground. The one that really kick-started the field was the IRAS, Infrared Astronomy Satellite, which was launched in 1984. And IRAS did the first all-sky survey in the far infrared. It was working out to wavelengths of 100 microns. And that showed us for the very first time that dust is a very important constituent of galaxies. So that really kick-started things. And at the same time, a number of countries, the UK being one of the leaders in this, was also pushing sub-millimeter astronomy, as it's called, from the ground. Now, sub-millimeter astronomy really kicks in at wavelengths of about 500 microns, essentially where Herschel stops. You begin to be able to see stuff from the ground. So, the most successful sub-millimeter telescope on the ground at the moment is the James Clerk Maxwell telescope in Hawaii. Happening in space at the same time, or over the decade after JCMT started, there was ISO, the Infrared Space Observatory, which is an ESA mission. That worked out to wavelengths of 160 microns. And most recently, we've had Spitzer, NASA mission. And there's also the Japanese Akari mission, also working out to 140, 160 microns. That's really a technology problem with the detectors. All of those space-based instruments, ISO, IRAS, Spitzer, Akari, use what are called photoconductors at the longest wavelengths. And the technology to do photoconductors at those wavelengths just doesn't exist. It's an extremely difficult thing even to push out to 160 microns. You have to do all sorts of tricks. With Herschel, we're using a completely different detector technology known as bolometers. Now, these are essentially very, very small, very, very cold thermometers. Literally, they're just temperature measurements. You cool them down to a few hundred millikelvin, a few tenths of a degree above absolute zero. And if you shine a little bit of light on them, their temperature rises a bit and their resistance, electrical resistance, goes up, which allows you to detect things. And bolometers, in principle, are sensitive to any wavelength of radiation you shine on them. The key problem with putting these on a satellite is to be able to cool them down to the very low temperatures that you need. And that's really the driving technology behind Herschel. There's a lot of technology and engineering in the background of Herschel, and science is really sort of the cream on the top for the results that we get.
And speaking of results, you said we have seen some images and there are yet more to come out. What are they really showing us?
Well, at the moment, the images show relatively nearby galaxies and show the dust in them to unprecedentedly high resolution. If you look at one of the nearby galaxies that we've observed with Herschel and compare with the best far-infrared image of that same object from Spitzer, and you can see the dust in the spiral arms, you can see some cooler dust between the arms. It's not the same as an optical image. If it was the same as an optical image, we'd be wasting our time going to far-infrared. But many of the same structures, like the spiral arms, etc., you can now see those and see how dust contributes to that part of the galaxy. Now, if you look at these images, they're available on the web. So if you go to the ESA website or the Herschel mission blog, which I run. So if you look at these images of galaxies, you see the nice big spiral galaxy, which is in the foreground, and that's really what we're focusing on. But you'll also see that the background behind the galaxy has sort of blobs in it. And you look at that at one of the wavelengths we get from our instrument, the Spire instrument. It takes images at three different wavelengths, 250, 350, and 500 microns. So if you look at one of those wavelengths, you'll see these blobs in the background and you think, oh, well, it's an early image, we hadn't quite got the noise suppression right. And then you go and look at the other images, and you see that the blobs are exactly the same position. And what we're seeing, even in these very early, very quick, very roughly reduced images, is these blobs are the background galaxies at much greater distances from the things we're really looking at. These are the background galaxies that contribute to the cosmic infrared background. And we're already seeing them in the earliest images that were taken with Spire on Herschel. And that just demonstrates the power of this instrument to tell us about what I've called the hidden history of the universe. And you can see it in the very earliest images, and that just demonstrates how sensitive it is, how well the instrument's performing. And now it's been tuned up. It's performing significantly better than in those early images. I don't think I'll be breaking any secrets to say that we're seeing these background galaxies much more clearly, and it's clear there's going to be a fantastic amount of new results on the cosmic infrared background galaxies and the early history of galaxy evolution and formation. That's really what the Spire instrument and Herschel were built for, to do these surveys of the early stages of galaxy formation and to understand where this 50% missing energy is going and what are the processes that drive it.
David Clements from Imperial College London on Herschel and the importance of far-infrared astronomy. David also runs the Herschel Mission blog, available at herschelmission.wordpress.com. This is Naked Astronomy, a new space science podcast from the Naked Scientists. We want to hear from you about what you would like to see included in this astronomy podcast. We're open to any suggestions, and for once, the sky is not the limit. Get in touch with any questions, feedback, or requests to astronomy@thenakedscientists.com. But now we return to Carolyn, Andrew, and Dominic to take on your queries about the cosmos. Firstly, we have a question from Risha Darmani, who asks, what are galaxies and what are quasars?
Well, let's start with a galaxy. A galaxy is a collection of around 100 billion stars. And for some reason or another, our universe seems to have kind of organised itself into these collections. So it's not as though the stars in the universe are just spread out nice and evenly. But for one reason or another, they've been grouped together, and when we look out at the universe, we can see around 100 billion of these galaxies, each with around 100 billion stars in them. And that's the universe that we can see. But as well as that, there are quasars. And quasars are quite a different beast. And we think they're powered rather than by stars, which come ultimately from nuclear reactions. The energy is coming from nuclear reactions in the centre of the stars. It's a very different kind of power. It's actually the power of gravity. And what we think is going on in these objects is there's a really massive black hole at their centre, millions times more massive than our sun, for instance. And as material is sucked in towards that central black hole, it actually sends out a lot of light. So ironically, even though it's a black hole, we see it glowing incredibly brightly because material, before it's got into the black hole, it's kind of bashing against itself, getting really hot, lots of friction there, and sending out all this light that we then see as a quasar.
Quasars have some quite interesting history to them because quasar is actually short for quasi-stellar object, which was a name given to them because they look quite like stars, but they don't have the kind of spectrum that you'd expect any star to have. And people were studying these in the 1950s and 60s. And eventually someone realised that these were actually remarkably distant objects that were moving at tremendous speeds away from us, which were redshifted by a tremendous factor. And so they are actually galaxies in the very distant universe, which are shining so brightly that they look like stars in the sky. And actually all you're seeing is the nucleus of the galaxy, which is this supermassive black hole, which is accreting material and glowing very brightly. And you don't see the rest of the galaxy because it's so far away that that's just faint and you can't see it.
And the really interesting thing is when you look at galaxies like our own and nearby galaxies, they all have these supermassive black holes in their cores, but they're no longer accreting. They're dormant black holes. And so we have this lovely connection between the galaxies that Andrew was describing in the nearby universe to these quasars that really dominate in the early universe, that maybe these are a phase that a lot of galaxies go through, when the supermassive black hole at the centre is actively accreting, and that maybe we're seeing a very early phase of most of the galaxies that surround us now.
So a quasar could almost be compared to an adolescent galaxy.
And is often done so, yes.
We've also had a question here from Stephen Sommerhalter, who says, why are there no planets that rotate perpendicular to the Earth's axis? He says he can roughly imagine how the rotation of the Sun's gravitational field causes all of the planets to revolve around the Sun in the same direction, but why would that stop them from spinning perpendicular?
Well, in fact, most of the planets in our solar system do rotate around the same axis, and it's just part of the continuity of all the material having collapsed down out of a spinning disk, a spinning nebula that formed the Sun at the core and the planets around it. But not all the planets rotate in the same way as the Earth. There is, in fact, the planet Uranus, which is completely tipped over. So instead of sort of spinning like a top, it's more kind of rattling along like a bowling ball. It has one interesting effect in that, like the other gas giants, it's got rings around it. But instead of being kind of more or less horizontal, these rings travel vertically around the planet. So it does look obviously different. And the reason that Uranus is different, we think it's back to when it was a protoplanet, still at a very early stage of formation. Maybe it had some huge collision that just knocked it over completely sideways, and that's why that one's anomalous.
And the early solar system must have been a very violent place.
Oh, there were lots of collisions and lots of things jostling for position around the Sun. And we've talked about the craters on Mercury. That is a relic of all these impacts of this early solar system, things colliding with each other really in this very, very violent first billion years or so of our solar system's history.
And we've also had a question here from Gregory McInnes, who says, do astronauts experience shorter days? He said he heard that clocks on the space station move faster than clocks do on Earth. And does that mean that the astronauts on board would experience a day that's actually shorter than 24 hours? He also said that if time is moving faster, does that mean the astronauts actually age faster as well? Andrew, what do you think?
Oh, now this is a tricky question because this takes into account not only Einstein's special theory of relativity, but also Einstein's general theory of relativity. So let's start with the first of those theories, that's the special relativity theory. Now, according to that theory, if there are two people, say there's me, and I'm just sitting doing nothing, and somebody else is on a train that's moving incredibly fast, then the rate at which time passes for those two people, for me and for the person on the train, would actually be different. And the person on the train would think that less time had passed than I would. So, for instance, in the time it takes them to travel from London to Manchester and back, for instance, if they were going really fast, they would think it had taken less time for them to do that than I would. That's special relativity, and it does in fact have an impact on astronauts because they're whizzing around very fast in their orbits in space. But we also need to take into account general relativity. Now, what general relativity is it's Einstein's answer to gravity, because he realised when he'd written down his laws of special relativity, they didn't quite fit with the existing laws of gravity. So he needed to rewrite the laws of gravity as well. Now, according to those rewritten laws of gravity, there's also an effect on time depending on where you are in a gravitational field. Now, the Earth has its own gravitational field, and we, down on the surface of the Earth, feel a much stronger gravitational field than astronauts who are up in space. So if you're an astronaut on a spacecraft and you look down and you see a clock down there on Earth, you see that clock running slower than clocks that are actually up there in orbit with you. And that's just an effect of the gravitational field. And it's not that the clocks themselves have gone wrong because there's different gravity. The clocks can be operating absolutely perfectly, but you still see it running slower down there on Earth. And it turns out that that is the dominant effect for astronauts. This effect of them going slightly faster isn't actually as important as the effect of them being far up and slightly out of the Earth's gravitational field. And that means when they come back to Earth, the amount of time that's passed for them, slightly more seconds than the amount of time that's actually passed for somebody down on Earth. If you think of them up in space, they're seeing the seconds going rather slower down on Earth. So they've experienced more seconds when they come back to Earth. So in fact, they're slightly older than they would have been if they'd stayed on the Earth.
When you say more seconds, we're not really talking about seconds of difference, are we? This must be a tiny effect, unless you're going close to the speed of light.
Yes, that's absolutely right. So it is an absolutely tiny effect. Of course, in this case, we're talking about gravitational fields. So it's not really to do with the speed they're going at. It's more to do with the strength of the gravitational field. And these effects only really become noticeable in incredibly strong gravitational fields. So, for instance, around a black hole. And in fact, if you sent your friend off into a black hole, you would never see them fall into the black hole. They would get closer and closer and closer to the surface of the black hole. But because the gravitational field for them was getting stronger and stronger, they would seem to slow down and down and down until eventually they just kind of stay there suspended in space as far as you were concerned. And you'd never see them actually cross into the black hole.
But that's only from your perspective. As far as they're concerned, it would only take a few seconds to
right.
disappear down.
They wouldn't be saved in any way by that.
No.
Okay, well, thinking of things that we send up into space and hopefully actually keep an eye on instead of lose into black holes, we've had a question about the things that we do send into space from Ryan Christensen. He said he had a question about these spacecraft, and he was reading about a new one that's being launched and noticed that in all of the pictures, it looks like the workers are going to great pains to keep things clean. They're wearing hairnets, they're dressed up really as if they were doing surgery. So why do they go to this extent to keep these things clean? Is it to protect the electronics, or are we looking to, make sure we don't let bugs into space?
Well, it's a bit of both. Obviously, you need to keep the electronics clean so that they're going to function well in space. But you're right, it is a question of actually keeping the instruments and the whole spacecraft as sterile as possible. And there are international protocols about how sterile a piece of a spacecraft has to be before you can launch it. And it is this fear that that we could cross-contaminate planets with bacteria or microbes from Earth. And it's particularly crucial when you think of all these poor spacecraft that are trying to find if there's any evidence from life on Mars. What we don't want to do is rediscover life from Earth that's been transported to Mars. And so there are stringent regulations about how many bacteria per square metre you're allowed to launch into space on your spacecraft.
And finally, we've had what I think is quite an amusing question from Ricardo Hernandez, who says, could we get more light at night time by covering the visible part of the moon with a highly reflective material? What do you think, Dominic?
Well, this is quite a funny question. I'm not sure why you want to make the moon brighter. Yes, I guess you could. The moon is already quite reflective, so you couldn't get much more reflectivity out of it. Of course, it would only make the nights brighter for half of the month, because the moon is only up in the evening sky when it's waxing towards full moon.
Apart from, as Dominic says, the question about why on earth we'd want to do that, so we have enough difficulty seeing the stars when there's a full moon out at the best of times, it would also be quite impracticable. I mean, we're having enough trouble getting missions to Mars, even perhaps potentially sending people to Mars in the next few decades. I think actually covering the surface of the moon with reflective material is way beyond our capabilities at the minute.
But I understand there is one or two very small mirrors on the moon that we actually use to monitor the way that the moon moves. We point lasers at them.
Indeed, and it's not just how the moon moves, but it's measuring exactly every day the distance between the Earth and the moon. And it's from those kind of experiments that we find the moon is still moving slowly away from the Earth. I think the rate's about 1 centimetre a century, but we can see that the moon and the Earth are gradually, very slowly, getting further apart.
So very small reflectors on the moon are very useful to us, but covering the whole thing with a high visibility jacket is probably not really worth the effort.
I think it's distinctly not on. And, as an astronomer, I'd rather see the craters on the moon than a nice big reflective surface.
That, at least, I think we can all agree on. Carolyn Crawford, Andrew Ponson and Dominic Ford taking on your cosmic conundrums. If you'd like your questions answered, then get in touch by email to astronomy@thenakedscientists.com. But that's all we have for this Naked Astronomy podcast. In the next edition, we'll be sticking with infrared telescopes to find out about VISTA, or the Visual and Infrared Survey Telescope for Astronomy. And we'll be learning about astrobiology, the search for life outside our planet. If you'd like to subscribe to the Naked Astronomy podcast, find us on iTunes or join us at thenakedscientist.com/astronomy. Naked Astronomy is produced by me, Ben Valsler, from The Naked Scientists, and comes to you from Cambridge University with support from its 800th anniversary team and the Science and Technology Facilities Council.
Thank you very much for listening to this launch edition of Naked Astronomy. There are more episodes of the programme available now and every month subsequently through iTunes. But to hear them, you need to actually sign up for their own feed. And to do that, you need to search for Naked Astronomy in the iTunes Music Store, or you can go to our website, which is at nakedscientist.com/astronomy. And the programme will be delivered to your computer for free every month. The Naked Scientists return, as normal, next week.